Hey guys, good morning. How's it going? If you are able to hear me loud and clear, just give me a sign. Say anything in the chat box. Hi, Alicia. Hi, Noel. Good morning, guys. As usual, set your chat to panelists and attendees. Yep. So just give me 1 second. I'm sharing my screen. Sorry for the delay today. We'll try and make sure that we start at 7 sharp. Moving on. Okay, here we go. So if you are able to see my screen, just type in PPT in the chat box. Great. So we'll just do a quick recap from yesterday on this slide because we are gonna, kind of like build on the information out here, right? So the OSI has 7 layers. It is a theoretical model. It is not something that you can actually see. We use this for documentation. We use this for explaining concepts, explaining how a protocol works, explaining how data goes from one part of the network or one system to another. How does the data flow? What are the different processes, functions? So to be able to explain this, we use. Otherwise, like if you compare OSI and TCP IP, TCP IP is a real world model. It is a suite of protocols. There are specific protocols which are implemented in the operating system, whereas the OSI is just something we use to explain the theory, and we use it for troubleshooting logic. That's it. So it has got 7 layers. The numbers of the layers are fixed. The names are fixed. So the topmost layer will always be layer 7 application, and the bottommost layer is going to be physical layer, layer 1. And whenever data is being sent, say for example, just give me 1 second. So if this guy is the sender and this guy is the receiver, so when data is being sent, there is always going to be an application. There will be some application. Now, what kind of application? This could be your email client. This could be a browser. This could be your chat messenger or whatever, what the day-to-day applications that we use, right? Maybe a Google Docs. So this application is going to take the data. It wants to send it somewhere. So maybe this is you, and maybe this is the Google server. So this application here wants to send data to Google. Maybe you're using Google Docs, right? Or maybe Gmail. So this application is going to take the data, send it to the application layer. Application layer will then process the data, send it to presentation. Presentation will process the data, session, so on, so forth, till data comes all the way down out the physical layer. Now, again, this is conceptual. There are a number of functions that happen on each layer, which we are going to take a look at. But the thing is that data passes from one layer to another, and in some cases you may skip some of the layers, but that is not I'm not expanding on that, so because that will serve to confuse you further. So for most part, just assume that data is flowing in a sequential way from top to bottom, and when by the time it is coming out, it is completely changed. There is a lot of information that is added to the data that came in. It was processed. The original data is not changed. The original data is there, but you keep adding a header and a trailer to the data like this. So here in this case, TCP, there is only a header. Like TCP layer, you add a header. IP layer, this becomes a header. There is no trailer. Whereas in case of data link control layer, there is a header, link header. LH is link header. LT is link trailer. So some information related to the data is actually inputted inside the outside the data. So the data in itself doesn't change. That goes send to the receiver, but it's like wrapping up a small gift into multiple boxes, smaller box and then a bigger box, bigger box, bigger box. So the biggest box is going to be here. So when this data is then flowing, maybe these two PCs are on the same LAN, the sender and the receiver, or they could be over the internet. That doesn't make a difference, right? So when the data is actually flowing from the sender to the receiver, when it comes to the receiver, it's going to meet the physical layer first. Physical layer is going to kind of unwrap what layer 1 out here wrapped. Layer 2 is going to undo what layer 2 did here. So if layer 2 wrapped it with a link header and a link trailer, layer 2 here will be unwrapping it and then sending it back up. I hope this is clear, right? So whatever this guy is doing here, that is information, control information, which is conveyed to these guys here, to the recipient. The recipient will take that wrapper out, read the wrapper, and then send the data up on top. So if IP layer added some header here, so this at the receiving end, that header would be discarded. After reading the header, you'll use the header information, discard it, send it to layer 4, so on and so forth. Is this absolutely crystal clear? What is happening? Why are we appending? Because we want to send some information here, conveyed to the destination, and the destination reads the information. It unwraps it, throws the wrapper, and sends the data to the next level up. If this is clear, type in clear. Awesome. So there is a name that we give to each layer of data. So when you talk about data at this level or this layer, we call it as, it is also called as L1 PDU. PDU stands for Protocol Data Unit. Just a technical term, doesn't matter if you don't care to remember it, but we call data at this level as bits. It's all zeros and ones. Data at this level is called as a frame. Data at this layer is called as a packet, an IP packet or a datagram. Datagram is the older name for it, but usually called as a packet. And at layer 4, it is called as a segment, right? And the process of wrapping the data when it is being sent out is called as encapsulation. And the process of unwrapping the data as it is being received is referred to as de-encapsulation, right? And when this same layer interaction and adjacent layer interaction is the adjacent layer interaction is when you're sending the data, this guy does its job and sends it to the layer below, then the layer below, and similarly layer 4, when the packet has been received, layer 4 is processing, removing whatever is there and sending it to layer 5. So this interaction between the top and bottom layers is referred to as adjacent layer interaction. Happens within the same system, right? Whereas same layer interaction happens across systems. Just something that you need to be familiar with. So what is an example of a same layer interaction? This guy will wrap something, this guy will unwrap something, right? So moving on. So what are the different functions that are important? What are the functions that we keep talking about? What happens when the data goes from layer 7 to layer 6 to layer 5 and so on and so forth? At the application layer, there are a number of protocols installed like HTTP, HTTPS, FTP, SMTP, POP3. So all of these protocols provide a particular function to the application. So maybe I have the typical example of an application is Chrome browser, right? Now, what happens in case of Chrome browser? It uses a number of protocols. Say, for example, I'm using a normal site. It will use the HTTP protocol to connect to it. Maybe I'm using net banking or social media. It will use the HTTPS protocol to connect to that particular site. So the application, which is sitting on top of the application layer, okay, listen to this carefully. The application is sitting on top of the application layer. It does not reside on the application layer. It sits on top of the application layer and asks for whatever it wants. And the application layer will then take this protocol and, it's a piece of software, it's a routine or a function. So that is given to this Chrome browser, which then uses it. So the application layer provides services to applications that sit on top of the application layer. Okay. Now, moving on. Presentation layer, it does a lot of compression. So if data is, huge in size, you want to compress it before sending, like compression. Presentation, if you want to change the format of the data. Encryption, if you want to encrypt the data in a way like nobody else in between has the ability to see what you're sending, right? So that is referred to as, presentation layer functions: compression, encryption, and presentation. And typical examples of presentation layer protocols would Telnet, We'll come to what telnet is. In fact, we have labs on telnet. And we will also talk about SSL, that is secure sockets layer. This is something that is used in HTTPS. So it is like HTTP is the normal protocol used for web browsing. When you add the SSL certificate to it, or the SSL protocol or the certificate to it, it becomes HTTPS. Right? So there is a newer version of SSL. Now this SSL that we are talking about is the older version. The SSL is no longer, safe to use. So we have all moved on to another version of SSL called as TLS. This is just for your information, transport layer security. So this protocol, SSL, TLS and all are what give HTTP the ability to be secure. Right? So whenever you're net banking, whenever you're doing social media or any secure browsing, and you see a lock icon to your, you see this lock kind of icon in your browser, so you are using HTTPS. And that comes from either SSL or TLS. And in today's time, it is only through TLS. Okay. Now, what is a session? A session is nothing but you open your, browser and you've logged in into Gmail. And for the time that it doesn't time you out, you are still logged in. The session is alive. So you can keep checking your mails every 15 minutes, 1 hour. So the server side, that is Google side, is still going to accept the fact that it's the same person who's logged in and they are checking their own mails. After some time, it will time you out. So this whole session management, that is creating a session, maintaining a session, and then deleting or destroying a session, that whole session management game happens at the session layer. So some examples of protocols are RPC, NetBIOS, and SQL. Right? So nobody is going to ask you to explain this. In case in an interview, they ask you to explain or give examples of what functions work on each layer. So you can mention the protocols or these protocols, or in some cases, there'll be hardware devices as well, which I'm going to explain. Right? So then moving on to transport layer. Transport layer is very, very important. There are a number of functions which happen on the transport layer. Now, this I'm going to explain in depth, right? So we will leave this hanging in here for a second, and we'll come back to this. I'll put a pin on this. Now, let's move on to the network layer. Network layer is where two important things happen. Network layer is where, first and foremost, a logical address is given to every system. That is, everybody will have a unique IP address. Whereas the second function that happens is, once I give an address to PCA, so maybe this is PCA and this is PCB, I have given them an identity. So that IP address would be something like 192.168.1.1. And this could be something like 192.168.1.2. So once they have a unique identity, when I say unique, it will be unique in that network. So in a particular classroom, if I have two people called Santosh, and the teacher calls out saying Santosh, then both people are going to look back at her and say, hey, did you actually refer to me? So, that kind of a confusion is not allowed. So you will have only one IP address, and that IP address will be unique for that network. So to give you a very simple example, can be a Santosh in this classroom and there can be a Santosh in another classroom, but that is not likely to cause any confusion. Right? We'll expand more on this when we do IP addressing, but this is just for you to be more familiar with the topics. Right? So you give everybody an IP address, unique one, that is logical addresses. Then you will determine the path. So if I want to send data from PCA to PCB from over the internet, there'll be multiple ISPs involved in between. So what is the path that you're going to take? Which routers you're going to go through? How will you send a packet from PCA to PCB? So how are you going to do that? That is the problem of routing. You call it as path determination. Path determination is a more, kind of like an old school term for it, but routing is the correct way. So on layer 3, there are a number of protocols which, like for example, Internet Protocol, which you already know about, and works on layer 3. ICMP, that is Internet Control Message Protocol. Now, this is a protocol which we use for troubleshooting. We will do something on this very soon, very. So, but to understand, like it's a protocol that works at layer 3 and it helps you ping systems. So you can send a test ping or a test packet from PCA to PCB. You can do a lot of diagnostics and troubleshooting with the ICMP protocol. So that protocol lives on layer 3. ARP is another protocol called Address Resolution Protocol. It lives on layer 3 as well. So these are examples of protocols, uh, examples of devices, hardware devices that work on layer 3 would be there is something called as an L3 switch. Don't worry about what an L3 switch is. We will have a session on that. And the second thing is routers. Routers are also devices that you can say that work. How do you say that? The way to say it would be, you can say that these devices work on layer 3 of the OSI. That is what it means, right? So these work on layer 3 of the OSI. Just give me 1 second, guys. I'll be right back. Okay, I'm back. So I was on L3 switches and routers. These are examples of hardware devices, right? Which actually work on layer 3 of the OSI, right? Now, layer 2 is data link control layer. There are two things that happen here. One is that we use something called as MAC addresses. We will see what MAC addresses are later. Think of MAC addresses of, kind of like somebody who's there, somebody like me, right? Is likely to have two names. One is name 1, which is actually used in my school register, in my certificates, and how the whole world knows me. And the other one would be a name 2, which would be kind of be like my pet name, which they will, my family and my loved people in my life and my friends are going to call me by that name. That is name 2. So think of a person having multiple names, right? So IP address is one of the names which you will use on the outside, and think of MAC addressing as a name which we use on the inside. Okay. So think of it that way for now until we approach that concept in more detail. So both are basically ways of addressing the same PC. So your PC have an IP address as well as a MAC address, but the functions are different and both are necessary. Both are not, a MAC address does not replace an IP address and vice versa. And there is also something called as a framing. Framing is nothing but creating a frame of data. Now, what is a frame of data? A frame of data is when you get data from layer 3, okay, and this data is there. At layer 2, I had a link. I will be adding a link header and a link trailer. That is all there is. That is framing. So examples of devices which work on layer 3 of the OSI, layer 2 of the OSI would be normal switches, LAN switches, also called as Ethernet switches, access points. Access points are very similar to switches. So if a switch is going to allow multiple, PCs to connect to it using Ethernet cables, that becomes a LAN switch or an Ethernet switch. Whereas if you have an access point, it's similar to a wireless router. So it is going to allow a lot of people to connect to it, just like a switch. Only difference is everybody is going to be wireless. So you can think of your access point as a wireless switch. It is also referred to as an AP or access point. Generally, from an industry point of view, we call it as an AP. And some examples of protocols that work at layer 2 as Ethernet 802.3 and WLAN, that is Wi-Fi 802.11. And finally, layer 1. Layer 1, what happens is you will only, layer 1, you can think of it as a dumb layer. Very dumb. I mean, it's so dumb that it does not have any intelligence at this layer. There is no intelligent work that gets done at this layer. So all you care about at this layer is the length of the cable. For example, for PCA to PCB, I'm connecting a switch in between. So what type of cable do I use? What kind of connectors would be there on the cable? So, what kind of voltages will run inside these cables? What will be the length of the cable from the PC to the switch? So on and so forth. So all of these things, what kind of signaling is going to be used? What kind of encoding is going to be used inside the, the cable for us to send the signal. Signal is always modified, modulated, and then sent from one point to another for a lot of reasons. So don't worry about why that is happening, but remember that it is happening. So what actually goes into it at the very physical layer of things? That is your voltages, your pin out. Pin out means, which pins are where. Modulation, signaling, the length of the cables, the voltages, everything at the physical layer is going to be your physical layer function. Typical example of this would be the physical cables, the Ethernet cables that we use. They have no intelligence. They just transmit data from one point to another. And then your connectors, if you can see, I hope you guys have seen a network cable before. That is the cable which is likely connecting you to your router right now, if you're not using wiring Wi-Fi connection, that is, but I'm hoping you have seen. If you're not, I'm going to show it to you anyways. So those kind of connectors, your telephone connectors, everything, every connector which is there, that comes at a physical layer. And your Ethernet cables come at a physical layer. Then hubs, there is something called as hubs, which is similar to switches, but they are pretty dumb, and we don't use hubs in today's networks anymore. In fact, over the last 10-15 years, we have never used hubs, but they are just there because Cisco wants you to learn them, and I'm probably going to help you understand them, but it's not really used in the real world, right? So just focus on this. I'm going to remove the text to the right hand side because that is like adding a lot of commentary. So I don't think it's really important for you to go so much in depth. So just focus on these functions. So if these functions are clear, type in F for functions. Great. I'll just give you a brief example of what actually is happening here. So step by step, how does the data flow? So there is an application which generates the data, and this application is usually sitting on top of the application layer. It sends the data to the application layer, and in some cases, the application layers might, depending on the protocol, they will add a header and a trailer and all that stuff. So they will add something. So your it adds an HTTP header to the data, and then this is optional, like I said, and then it sends the data from the application layer to the presentation to the session, and then I've omitted those here. Then it comes directly to the transport, right? So all those layers will be passed, and then it comes to the transport, and then don't think that the application layer is directly going to the transport. It is coming through all the other layers, but for the sake of simplicity, I have included only these layers here. But actually, it will be going through all the 7 layers of the OSI. Okay, so once the application, the app's data, the application that you're using, that data goes to application layer, it will add an HTTP header because you're browsing maybe, so you need HTTP or HTTPS, so it will add an HTTP or an HTTPS header, and then send it to the transport layer, right? And then the transport layer is going to add a TCP header and then send it to the network layer, which again is going to take all of this data which has come from top as one piece of data, and it's going to add its IP header. And then this data flows down as one unit, and at the frame level, there is a data link, header and a data link trailer. So it is going to encapsulate. You see the first word everywhere is encapsulate, encapsulate, encapsulate. And when it comes to the physical layer, when everything is done, the layer does not encapsulate. It takes everything and transmits the bits as a series of zeros and ones. The physical layer, now for example here, the physical layer does not care. None of these layers in between care what the application is. The application could be Google Docs, it could be, I don't know, it could be n number of things, but nobody really gives a damn. Nobody cares, because each and every layer is independent. Like I said yesterday, this guy will do the job, pass the file to this guy, he'll do the job, pass the file to this guy, so on and so forth. But this is just an example to illustrate. Now, TCP IP versus OSI, I have already explained this in very brief terms. The one thing that you need to remember from an exam point of view is they call the OSI as a 7-layer thing, which we have seen now. TCP IP, on the other hand, they call it as a 5-layer model, right? So everything is the same, transport, network, data link, physical. The only difference is the top layers for the OSI, that is application, presentation, and session, are condensed into a single layer called application and TCP. So we are comparing both the models, the OSI model and the TCP model. So the only difference in TCP is the top three layers are gone. They are all replaced by a application layer only, and there are like 7 layers of the OSI. There are only 5 layers for TCP IP model. Now, OSI model per se is strictly theoretical. We use it to describe the flow of data, how something works, so on and so forth, troubleshooting logic and all that. Whereas the TCP IP model explicitly specifies which protocol will do what. DHCP will do this, DNS will do this, HTTP will do this. So it's practical. It's practical and it is implemented within the operating systems everywhere, be it Windows 7, Windows 10, Windows 8, or maybe an Android, or maybe a BlackBerry mobile, whatever it is, right? It will have this piece of TCP IP code within it so that it can accept an IP address, be a part of a network, and let you connect to the LAN and the internet. This TCP IP model, the 5-layered model, is also called as a Department of Defense or a DoD model. Now, all the vendors conform to TCP IP. So it fits together like a jigsaw. Like I explained in one of my earlier slides, if everybody is talking the same language, then communication is not only possible, it's also easier. Right? In this case, what happens is it is not just two PCs which are talking the same language, but all the devices which are there in the network. Maybe this guy is part of a network which has a switch. So your cables are built to specifications, your network interface card or Ethernet port on the switch, on the PC, then the switch with ports, everything has to be aligned along, TCP IP. Everything will be designed with TCP IP in mind. That is why they're able to talk to each other, right? If you want to learn about any TCP IP protocol in depth, go and search for RFC documents, RFC TCP document, RFC IP document. Those documents sound very complex, but they are incredibly easy to read. They are kept as notepad files on the internet. So they are very, very easy for you to read and learn from, in case you're interested. Okay, I had promised you that we would discuss some of the main functions of TCP. Right, I'll just have a sip of water. Just give me 1 second. Okay, so if we are clear so far, just type in clear in the chat box. If you have any questions, please feel free to shoot. Okay, so this next part that we're going to look at is going to be about the transport layer and specifically TCP. Now, the transport layer generally has, just give me 1 second. This card. Okay, so here, like I said, let me just remove this portion. So when I give you the notes, it does not confuse you. Okay, so yeah. So transport layer, that is layer 4 of the OSI, has layer 4 of the OSI has basically two types of protocols, two big protocols, big game protocols. One is TCP and one is UDP. These are the major protocols that are used at layer 4. Now, what is the difference between them? We will get into an in-depth session on them probably today, the second part. TCP is more reliable. UDP is more real time. So there is a guy, imagine this as a person who does things slowly, but they get it done for sure. But sometimes you just need somebody to do a quick job, somebody to just run around and do it quickly instead of somebody, sitting and, just, doing a perfect job of, sending the data or whatever. So that is where you need UDP, right? So there are some other differences as well. So I will explain to you some of the functions that happen at layer 4. Okay, so now imagine there is a PCA and there is a PCB, right? So you want to send data from A to B. Now there could be a switch in between, or there could be a cloud in between. When I say switch, it could be a direct LAN, both are part of the same LAN. Or maybe they are connected to each other over the internet, does not matter. So our point is that PCA wants to send data to PCB. So if you want to send data reliably, think about it. So what happens is there'll be a number of packets of data. All the information will not be contained in a single packet, right? So all the packets of information which need to be sent. So any data that I want to send, maybe I want to send a web page, maybe I want to send a request for a web page, maybe I want to send some files. Everything is going to be, digitized into small packets, IP packets. Now, each and every packet, it will be sent across one at a time and received by PCB out here. But what happens is, because of the nature of how internet actually works, there is no guarantee that, especially over the internet, that these packets, let's give them virtual numbers just like that. There is no guarantee that the path taken by packet 1 is going to be the same as the path taken by packet 2, 3, 4, 5. So it is very much possible that one of the paths goes through XYZ ISP and it reaches faster, and some of the other packets actually reach later. So if we don't number these packets, and PCA sends them in the right order, but because of some delay in between, they come in different different orders at the destination. The best example is, I don't know if you guys used to watch this Amazing Race. There is a series called as Amazing Race, I think, on AXN. They used to have these races, like couples would be there, and best friends and all seasons. So there'll be a number of people who are starting out. They'll be in groups of 2, so you can go along with your best friend, and you would be going from place to place like a treasure hunt, and doing stuff, and then completing the tasks and moving on forward. And eventually one person wins, like I don't know, maybe like $1 million or something. They win a lot of money. So the thing is, everybody starts out at the same point. They have the same resources, but some people reach faster and some people reach slower, right? So somebody comes first and somebody comes last, right? Because of the path that you take, something very similar to that. So if you don't number these packets with sequence numbers, I call them as a SN, sequence number would be there for each packet. If you don't put that number to the packet, then when it arrives at the destination, do you think the destination will be able to tell which packet is first and which one is second? No, right? It is not. So there'll be a sequence number or a number attached to uniquely identify each packet that is being sent from PCA to PCB, and vice versa. So that is called as a sequence number. And if a packet, so what is the point of a sequence number? The point of a sequence number is that the destination can rearrange or reorder the packets if they come in the wrong order. Point number 1. If the destination gets packet numbers 1, 2, 4, and 5, it does not get 3. The destination can actually ask PCA back, hey, where is packet number 3? And then PCA will realize that for some reason, hey, I sent it, but I think you did not receive it. So let me send it again. So it will retransmit packet number 3 only to PCB. That is because of sequence numbers, you are able to reorder the packets. You're able to see which packets were received, which ones are missing, then ask for a retransmission. Why retransmission? Because TCP is a reliable protocol. I'm talking about specifically about TCP. Now, this thing which you're discussing here, that thing does not happen in UDP. Why? Because UDP is not reliable. It does not need to do this. So if a packet is dropped in UDP, it is dropped. It is dropped. That's about it, right? So it is not going to be retransmitted and all that. So in TCP, you're going to ask for the packet to be retransmitted because TCP is known for reliability, right? So you will retransmit when somebody asks you, hey, this packet was not received, it got dropped. You will retransmit it. And if there are any problems with the packet, again, retransmit, packets lost, again, retransmit. That is possible because of the sequence numbers. And for each and every packet that a sender sends to a receiver, there will always be an acknowledgement from the receiver back to the sender. Always remember this. Because now the sender has sent 1, 2, 3, 4, 5 packets. So how does the sender know that the receiver has received all the 5 packets? Right? So the receiver will be sending an acknowledgement to the sender. And there will also be something called as flow control. What is the meaning of flow control? Now, suppose, to give you an example, imagine there is like, there is a huge pipe. There's a huge pipe which is like flowing with water, And what you have is a small bottle. You want to take this bottle and fill it up with the water. But the problem is you can only, the bottle's neck is going to be the bottleneck, literally, right? So the size of the neck of the bottle or the opening of the bottle is the maximum it can be. So it can only take in X amount of water at a time. What happens if this overflows? It keeps pouring water, and this can only take in, maybe this is pouring water at the rate of 1 liter per second, for example. This guy can only take in maybe 100 milliliters per second. Do you think a lot of water is going to be wasted? So if there is a way that you can tell the owner of this pipe, or maybe the municipality guy or whosoever it is, right? So maybe you can tell them, hey, we can catch water only at this speed. Maybe this is a bucket for all I care, doesn't matter. So you tell them, hey, this is the speed at which we can catch. So if you're going to send more, data is going to be wasted, rather water is going to be wasted. So please don't send more because overwhelming me. Does that make sense? That part where the sender is sending something to the receiver at a very high speed, so maybe 1 Gbps or 100 Mbps speed. 1 Gbps is 1 gigabit per second. That is the equivalent of 1000 Mbps per second. So if this guy is sending at the speed of 1 Gbps, but this guy has an older network card or a smaller internet or a slower internet rather, and he can only accept speeds of up to maybe 2 Mbps, right? So do you think a lot of packets are going to be dropped? Yes. Do you think PCB needs to come and tell PCA, hey, please slow down? That is, my friends, is referred to as flow control. So when you give numbers to the, it allows you to reorder them. It allows you to retransmit in case of loss of packets. There is always acknowledgement from a receiver to the sender, and there is always flow control where the receiver tries to control the rate at which a sender is sending information. So these are all good features to have, solid, reliable features to have. In fact, if you look at these features and you put them into a, say, hey, this is a good guy, he's a good guy, he's a reliable guy. That is TCP, right? This is clear. I had some diagrams and all, but they're all from the textbook and all. They're pretty complicated. So I have taken the liberty of not including those and only explaining these concepts with my own drawings. If it is clear, just let me know in the chat box. Type in C for clear or clear for clear or whatever vibes with you. So, okay, great. So this is TCP. Now, these functions that we spoke about, these are not available in UDP, right? So I'll come to the concept of multiplexing using ports. I'll come to this. I've not explained this. I'll explain you this briefly. Error recovery, if a packet is gone, how to request it back again. Flow control, how to establish a connection, order data transfer, data segmentation. Okay, segmentation, I'll just briefly explain, and ports I'll explain. Ports, in fact, we have a separate session on it because it's pretty important for you to No. So all of these are not done by UDP. The only thing that UDP does is it segments the packets. That's all. Because it is more real time. Okay, before we move on to TCP versus UDP, let me explain what segmentation is. Simply put, you have a big, maybe slice of cake, right? And you want to give it to your friends to eat. You're going to slice it into smaller parts, right? And put those onto a plate and then maybe give it to your friends, right? So this is segmentation. When there is a piece of data or there is a file or there is a packet which is too big to pass from one network to another, you will break it up in smaller parts or smaller segments and then send the data over. This is nothing but segmentation, and segmentation is done by both TCP as well as UDP. Okay, so that is one concept of segmentation. The other thing is, see, whenever PCA is sending data to PCB, whenever data is being sent from PCA to PCB, again, there could be a switch in between, or maybe it is over the internet, doesn't matter. What happens here is PCA is not sending to PCB. Now listen to this carefully. There is an application, say let's call this application 1, which is sending data to an application, that is application 2 on PCB. Does this make sense? An application is communicating with another application. So when you open, connect to Google using your Chrome browser, so your Chrome browsers, that particular tab is communicating with the Google Chrome, Google Gmail server, or maybe Google search, right? So you can't say that your PC is connecting to another PC. You can say your application on the PC specifically is connecting to a specific application at the remote end. Is this making sense so far? Because this is the concept of ports. Now, how do I identify this application here? How do I identify this application here? That I have a number given to them. I refer to as a port number, right? So why do I need a port number? Because when I'm sending the data from this system to this system, IP address is there, IP1 is there, IP2 is there. I'll be able to reach the machine here. But inside this machine, which particular application do I need to give the data to? There are like likely thousands of applications here. So I need to know the port number of this destination machine. So that will tell me the combination of the IP address. It's like the IP address is like the building, and the port number, think of it as the flat number, or maybe the person living in a flat. So if you find the building, that is not enough. You need to know exactly where to go to deliver the correct parcel, right? So this is kind of like that. So communication will go from this point to this point, building to building, but then here it will go to a specific application that will be identified by a port number, which will be unique for that application. Similarly, when this guy replies back to this PC, the data again comes to this PC, but then again, like you may have like 20, 30, 40 applications running. Which application will get the data, the returning data or the reply from the remote PC? That is why you need to identify this application as well, the sending application and the receiving application. The sending application, you can call it as a source port, because it is a source, right? This is where your data is being sent from. And this is the destination. So we call it as a destination port number, right? So more on this later. I will explain you with more examples. So don't worry about it. Just to tell you. And this port game, the game of ports, like the Game of Thrones, this game of ports actually happens at layer 4. That is why I am actually discussing it. And it is applicable to both TCP as well as UDP. So, clear so far? If you're clear, just type in C. Any questions, feel free. Okay, so no questions so far. So either I'm doing a fantastic job, or maybe you guys are not paying attention. Just kidding. If you have any questions, just let me know. That's completely fine. And just make sure, make it a point to revise every single day. At least you'll be able to do it probably from the time I give you the notes. I'll send out the notes in the WhatsApp group. So just start going through the notes. It might take me some time to modify it, but I don't want you guys to wait for it. So just start revising from the notes and let me know if you need any help, right? So TCP versus UDP. So you guys want a small break before we move on to another major topic? If you want to break, type in yes. Yes, sometimes this becomes a little intense because you're bombarded with a lot of new information. So you should take a small break and then get back to it. So 1 second, the time is exactly 8. So let us meet. Let's meet in 5 minutes. Okay. And again, I've kept mine to all panelists as well. So I'll see you guys in. Hey guys, I'm back. If you're back as well, let me know in the chat box. Okay, Noel is back. How about Alicia? Yeah, great. So I'm assuming you're still able to see my screen. If yes, please confirm back. With a yes, maybe. Okay, so great. Okay, so TCP versus UDP. TCP is the full form is Transmission Control Protocol. UDP, which is an abbreviation for User Datagram Protocol. TCP is more connection oriented. So what it means is before two PCs can communicate using TCP, there will be a connection which is formed. So when there is PC A and PC B, if they want to do a TCP session between them, there'll be a connection which is formed, a session which is formed, and then A and B will exchange data. That is why we call it as connection oriented. That is why, because there is a process of establishing a connection, data is transferred, exchange is done, and then you break down the connection. That takes time, right? Because you're forming a connection and then kind of like, so that is why it is a little slower. And also it is slower because data is lost. This B will then ask A to resend the data will be resent, reordering and all that. So a lot of processes are involved which make it slower. Whereas UDP on the other hand is very, connectionless. There is no connection established. So between A and B, if you just want, hey, this guy sends the data, this guy receives it. If the packet is dropped, then this guy can request again and then probably get it back later. Right? If the packet is dropped, it is dropped, but there is no way that you can. In fact, it'd be wrong of me to say that the packet could actually be received by B requesting A again, because if A sends and B doesn't receive, then that's it. There is no. So A has to resend it back again. Think of it that way. It also makes UDP very, very fast. Right? So TCP is all about reliable communication. There'll be a lot of acknowledgements from the receiver to the sender for every packet they receive. And if a packet is lost, there'll be a retransmission or redelivery. And also ordering of packets is there. So if packets are sent in a particular order, they will be reassembled into the correct order at the destination or the receiving end. Right? So some examples of protocols which use TCP are HTTP, FTP, and SMTP. HTTP is used for browsing, FTP is used for file shares, and SMTP is used for emails. So usually we use it. We use what we call as TCP because we need reliability. We need things to be a little slower is okay, but we wanted them to be more reliable, right? And it is preferred by applications requiring reliability. For example, internet banking, social media, wherever you want reliability, that is where you have reliability, right? So this is one thing. Now, user datagram protocol, there is no reliability. In fact, there is no guarantee at all. You're just guaranteeing a fast throughput. Think of this TCP as a blue dart way of sending packets from one place to another. People will not steal, people will not break the parcel, they'll handle with care, but then you pay a premium for it. Whereas UDP is more like, your local courier agency who's just going to dump your load on a top of maybe a Nita Volvo bus and just send it from one point to another, and you don't know if it is going to reach. If somebody takes a fancy to that parcel, it's gone. And if the recipient gets it, God knows in what condition they're going to receive it, right? So applications like DHCP, DNS, TFTP, these protocols, they use UDP. And these are usually preferred by applications which need real-time performance. Say, for example, video streaming and all that. A connection-oriented protocol, connectionless protocol. Yes, we have already covered this. So what are the three stages of connections? What are the three phases in which a connection is actually established for TCP? Obviously, in UDP, there is no connection. We are only talking about TCP. There, the client and the server is there. Client is always going to be you who wants a service or wants a resource. Server is going to be the one who provides a service or provides a resource. So if you're connecting to google.com, Google is the server and you're the client. So you will be sending a special packet called as a SYN packet, also called as a synchronization packet to the server, right? And the synchronization packet, when received by the server, it tells the server like, hey, I want to connect to you. Server sends a synchronization acknowledgement packet back, SYN ACK packet back to the client saying, hey, yes, you can connect to me. Now the client again does a third packet, sending an acknowledgement packet saying, hey, I received your acknowledgement that you're allowing me to connect to you. So that's great. Let me connect to you now. Right? It's a very formal way of doing it. If you look at it like a formal interview kind of. Hey, I'll give you an example in the next slide, in fact. See, hi, I would like to talk to you. Okay, sure, let's talk. And then third part is, okay, let's do this. Let's talk now. Okay. So kind of like A asked B, hey, are you, can we go out to have pizza? Maybe you say, okay, let's do this. Okay, let me, make a plan and let's go for pizza today. Kind of like a double confirmation. Right. So this 3-step process is called as a 3-way handshake in TCP. So before data gets transferred from point A to point B using TCP, there will always be a 3-way handshake. And after this is successfully done, then only data is going to be transmitted. Please bear this in mind. Whereas for UDP, it is pretty simple. Client is going to make a request to the server responds back. That's it. Request, response, nothing else. Right? There will not be a connection established, a session established in case of UDP. Right? So your TCP is actually a connection-oriented protocol, ensures the establishment of a connection by means of a 3-way handshake before any data transfer takes place. This is exactly what we just discussed. So it is a special packet called as a SYN packet, I said. But if I have to go a little in depth, I'll say that it's a normal packet. And the normal packet, there are many control bits which can be set and reset. Special, places where I will set this to, if it is 0, then it is off. If it is 1, as in the binary, it would be on. So I'll set a bit to 1. There's a special bit called as a SYN bit in a packet. So I'll set that bit to 1, a value of 1, so that it becomes a SYN packet, and then the server gets the SYN packet. Similarly, there'll be a SYN or ACK bit which will be set when the server responds back. So when you say a SYN packet, it's not a special type of packet. It is just a regular packet where the SYN bit is actually set to 1. So it is turned on. It's like you're turning on a switch. So SYN bit turned on, SYN ACK bit turned on, ACK bit turned on, you're done. Now data transfer can happen between the client and the server. Okay. So the thing is, I'll keep this very simple, during the initial process, right, of exchange of data back and forth and all that, data, between A and B, or maybe this is your web browser and this is the web server, Google web server or Facebook web server. Which ports are we going to use? That data is also exchanged, and that data is also kind of like noted down. So this guy will come to know which port is this server going to use, and this server will know which source port this guy is going to use. So you will exchange port numbers also during this phase, during the connection phase, when you're setting up a connection. And the last but not the least, when you're disconnecting, you will need to disconnect, in a similar fashion. You can't just, plug it out. So there will be a 3-step process to disconnect, where you send a finish or a FIN bit. Again, the client will initiate, because the client has a requirement. The server doesn't care. It is on all the time. It can accept as many connections as you ask it to handle. But the client, when the job is done, it will disconnect. So when that happens, the client will send a FIN bit, a packet with a FIN bit set to the server. The server will then send a FIN ACK bit, and then there is an ACK bit. Very similar to the process here. Only thing is, this is for establishing a TCP connection, and this is for disconnecting a TCP session. Clear so far? Any doubts? Any confusion? Okay, clear, great. So I think we will end it here today, because this again is a topic you'll need some time. I won't be able to do justice to it today within the next 15 minutes. So logical ports we will take up tomorrow. Okay, if you have any questions, you can ask me based on whatever it is that we have covered so far, or we can call it quits for today and catch up tomorrow. Any questions or no question? If there is no questions, tap in NQ. Okay, great. So I just wanted to quickly ask you guys, is it easier for you, the level at which I'm teaching you right now, the terminologies? Am I making it simpler for you, or are you, finding it difficult to, maybe I'm not giving you enough depth in the topics so far? I mean, 2 days. Today's the 3rd day, but the first day was an introduction. Okay, great. Noel says it's easy, and Alicia is saying it's good. Great, no problem. So we will catch up tomorrow, guys, and we will continue on with this. And for this first week, because it could be a little overwhelming, I would not be doing a Saturday, but otherwise, probably from the next week, we'll do a Saturday as well, because it's just 1.5 hours in the morning, right? So, and you will have plenty of guys throughout the day, right? So thanks a lot. I will see you tomorrow. Take care, and bye-bye. Thank you, Noel. Thank you, Alicia.